Hello. Well, we're going to start the exciting first video. Hold on a second. Maybe not quite as exciting as I thought it would be. This is going to be about homogeneous data structures. These really are all vectors, but we can think of as vectors, matrices, and arrays. Okay. Well, the basic idea is everything is going to be based on a vector, and a vector happens to be, just think of it as a sequence of little containers, all of which contain variables or values of the same type. And when I say type, it's either integer, logical, there's a lot of types, but the main ones are logical, which are either true, false, which can be thought of as 1 or 0. There's integers, there are real numbers, which are double, and then characters. And it's going to turn out, when you have a vector, everything in the vector is going to be of the same type. There's a few commands that go with vectors, basic vectors. There's combine, which is used to create vectors. There's length, which will tell you how many things are in the vector. There's type of, one of the probe type commands. This works with lots of different objects in R. Type of tells you whether what's in the vector is an integer or such. Class, which I believe will be numeric for just a straight vector, but tells you whether something's been given structure as a matrix or an array or something else. There's attributes. So these are all used for probing the properties of a vector or an object. Attributes will tell you what attributes are. What an attribute is basically, you can think, I'm going to use the word basically way too much. A vector is a sequence of values, little containers for values, and all the values are of the same type. But along with that sequence, there's kind of, think of a little sticky note stuck to the side of it that is sort of metadata that tells you things about that vector. And those are what the attributes are. The attributes in general, there's a lot of very important ones. One of the key ones is, well, there's names, which give you names if you want to name each individual object. That ends up being an attribute. Another attribute that's used a lot is class. Pretty much everything has a class attribute attached to it. But other objects have other attributes that tell you something about those objects. So we will look at some attributes of things. And along with all of those, there are some specialized functions to probe vectors. The is. So you can ask, is logical? To see if it's a vector of logicals. Is dot character. Tests if its characters. Is numeric. Tests if it's numeric. What a shock there. All right. Going with each of the is's, there's also as commands. As logical or as numeric. What those ones do, the as commands will force a vector into a specific type. So if it's not already numeric, it'll make it into a numeric vector. Well, we'll see how those work. There's also things like as integer, and so on. Okay. And then finally there's str, which tells you the basic structure, and that works for any object. It'll tell you what's inside that object. And of course, finally, there's the one that you use all the time without even thinking of it. If you type just the name of an object and hit return, you're actually running the print function, which gives sort of a controlled output that whoever wrote that particular object type will use the print function to control what the program shows you as far as what's inside that vector or object. Okay, let's try this out. I will create one. We'll use concatenate. Well, that looks good. I'll take a print of it. There's that. So the type of it is double. So it's real numbers. I could have made one of integers. Let's do that instead. By the way, I'm using an equal, and you can't stop me. Okay. Integer. Right? To look at the basic structure of a vector, you'll see all it has is there's the type. It's 4 objects numbered 1 to 4, and here's the actual values inside of it. Okay. And you probably all know this, but to get to any particular one, like the third thing in the vector is x3. All right. I'm not going to go into subsetting much at this point, though, because it can get pretty fancy. Let's see. So we've tried structure. So class will tell us that x is a integer. Actually, it's a vector of integers. It certainly should be numeric. Yep. Oh, but it's not a vector of characters. Okay. If I wanted to make x into something other than integers, I could do this as as double. I don't know if it'll do as double, if it'll just be as numeric. Now I've got to see this. I'm dying of curiosity. Ooh, it worked. Okay. It sort of looks the same, but if I do type of, I will see that I've converted it all to real numbers in there. Okay. So let's try to think about one concept, which is coercion, that works inside a vector. So let's look at our vector again. And by the way, I can make vectors by stacking all sorts of, using, I guess you'd combine the combine command. So I could combine the old variable x with some new vectors. There's one. Here's another one. Now you'll notice what's going to happen is, because all things have to be of the same type, there's going to be coercion. We have a mixture of some, x is now doubles, so I think these are all going to be doubles, other than this one, which is character. So logical and integer are the most restrained type of variable. Then there's reals, and then, which are double, and then there's characters. So for instance, if I put a single character in there, it's going to convert everything to characters, because that's kind of the loosest sort of variable they could or type that they could put on it. So let's look at what XX looks like. Ooh, look at that. Everything's been converted to characters by coercion. If I do type of, I will get that. Yep, it's all characters. Okay. And class character, if I look at the structure, yep, there's characters, there's 10 of them, and there they are right there. You might think, well, what if I try to force this to be integers? What will happen? What will happen? Well, we'll tell you what, it'll do the best it can. So 1.1 is probably going to be truncated. A character can't be turned to an integer, so it'll probably end up to be a missing value, which is NA. So let's just try it. Y equals as integer. Ooh, look at that. Didn't like it one bit. So you see it truncated the one value and it put an NA for the no. And if we look type of, you'll see it's an integer. And yep. Yep, certainly is a vector. So, enough on that. I should tell you something funny about the missing. So, the NA. So, you know, there's a lot of, in vectors of numbers, there's actually a lot of things you can substitute in. There's a INF, which stands for the number infinity, which you'll get by dividing a positive number by 0. There's actually a negative infinity, which can be validly put inside a vector. There's NaN, not a number, which is which is generated sometimes when you do a numerical calculation that's indeterminate, like 0 over 0. See, if we try 0 over 0, we'll get NaN. And then there's the missings, Na. Technically, missing should be used for when one of the spots in a vector or data structure is unobserved. So it's used for like tables and things that are missing pieces of data. Here's the funny thing. NA actually can, generally it doesn't do any coercion, because that would be horrible if you stuck an NA in your data set and it coerced everything into a specific type. But there actually are NAs that have types. So if you look at this, there's an NA, and oddly enough, that's then a missing integer. So NA of integer. Oh, you know, one thing I haven't done. Well, let me finish up this first. You can have NA character. So you'll notice it's kind of funny. Not that anyone sane would do this, but if you put an NA in there, I could coerce. Ooh, let me make all these integers. I'm very easily entertained. Okay. Actually, without saying integer at all, you know, the default is for it not to coerce. So everything's happily an integer. Also, if I did this, okay, that's a missing integer. It's going to be the integer. But watch this. I actually could make a missing character. Should give you an idea of the concept of coercion. So even putting a missing value that's been said to be a character is going to, well, guess what? Think about what's going to happen here. By sticking in a NA, which I declared to be a character, I essentially got a coercion going on. Now, one thing I haven't used so far is attributes, because these don't have a whole lot in the way of attributes. So let's look at one of our early ones, like X. Yep, not much going on there. Null means nothing. Yeah, null is actually in addition to those other. Oh, let's go. That's a good question. What type is inf? Oh, okay, it's a real number. Huh, gee, I wonder if you can have an integer inf. Sure. I am horribly easily amused, aren't I? Nope, didn't like it. Okay. I thought it was worth the gamble. So, let me see. We were going to go... We've looked at print, we've looked at... So let's look at a somewhat more complicated data structure. The matrix. It turns out a matrix really is a vector. So let's just see. And when you create it a lot of times, using cbind works, or rbind, but we're going to use matrix for now. So and then we put a vector in there. Let's see what it looks like. Sure looks like a matrix to me, but really it's a vector. So this vector right here has been actually done one column at a time. So by the way, if you want to put in row by row, one row at a time, you need a command by row equals, or not command, argument by row equals true put in this function. So you actually go down the one column, fill in, and then you go down the next column, and so on, filling it in. So it's really a vector. What it really is a vector that has a class set to... So remember, you have a vector, which is a bunch of containers containing in this case, I think, doubles. Let's see. Yep, they're containing real numbers. So we've got a vector of length 6. So you can see that's what it is, the vector. And in order to make it into a matrix, what happens is the class attribute is set to be matrix. And it gets another attribute, which is dimensions. So another attribute is attached to it. We can see it a couple ways. If we do attributes, we'll see the attribute it has, other than its class being set, is dimension. So that tells it there's three rows and 2 columns. We could also get this just by looking at the structure. So notice it's numeric. This tells it that it's 3 rows and 2 columns. And here's the vector of data that's in there. Because it really is a vector, you can actually treat them like a vector. So I could just say W and pick the 5th thing out of W, which what would that be? Well, if it's a vector, 1, 2, 3, 4, 5, that's going to be the value 6 right there. Yep. I'm just astounding, aren't I? Just knowing the future. Okay. Which happens to be the same thing as if I use it with vector subscripting. So that's second row, second column is 6. What a shock. Okay, let's see. What do we use? Did I try a type of on this one? Yep, we've done type of, we've done class, we've done length. We've looked at its attributes. Coercion, because it's really a vector, you have to be careful. Because a matrix, if you change one thing in the matrix, it won't just affect that column. It's going to change the type of the entire matrix. This occasionally causes big trouble in programming. So let's see. You never want to put different different types of variables as columns in a matrix. Now let's pick one of these. Let's go W of 1, 1. If you set it equal to no, now I look at it, I've suddenly coerced every single value into being a character. By the way, I have to be careful in switching it back. I might think, oh, I could use as numeric. Well, as numeric might not do quite what we want, because the trouble is, as numeric will want to take the characters and make them into numerical values. That's fine. It'll convert the no to an NA. That's fine. But some of those as things might strip the class or the class away from it. So I'm kind of curious. Let's see. WW. Let's do as numeric. Yep. So far it looks good, but when I print it, look, I certainly have converted to a numeric, but I've also stripped away the matrix class. It's been output as a vector. So that you really see its vector nature at this point. I know I'm forgetting something critical. I just don't know what it is. I guess that's the definition of forgetting something. Okay. And again, I think I didn't look at the structure. Let me recreate this matrix. Okay. Oh yeah, we did look at the structure earlier. In a similar vein, if you want a matrix, analog of a matrix that's in more than 2 dimensions, you can go to multidimensional matrices or arrays. So let's go to array. Here with the array you put in numbers. I'm actually going to put the numbers 1 to 10, 21 numbers from 1 to 10, equally spaced. And so 21 numbers. Ooh, that's not a nice divisible value. So 20 numbers. I'm going to get weird values though. Oh, no, I won't. No, I won't. That'll work. Okay. And then I pick the dimension. So this is going to generate a vector of values, and then I'm going to give it, like, the first dimension is going to have 2 possible values, second dimension 2 possible values, and the third dimension 5 possible values. Oops. Okay, so let's look at what this looks like. You can see here's the first dimension, the row in each one of these ones. Column is the second dimension, and then which of these slices through it, that's the third dimension. It has values 1, 2, 3, 4, and so on up to 5. So for instance, QQ of 1, 1, 2, or is 1, 2, 4, is going to be the fourth one of these matrices, second column, and first row. So it's going to be 7.63. Yep, not a shock there. Just like before, if I change a single one of these values, so to a, well, it's a vector. So I could just treat it like a vector and say QQ of 3, and it'll give the third value, 1, 2, 3, right there, if it's being treated as a vector. Because as a vector, it's going to go down this, and then it's going to add these ones, and then these ones, and these ones, these ones, and these ones, then these ones, and then down this column. So it really is a vector with attributes. I'll bet the attributes are dimension. Yep, there we go, 2, 2, 5. Or if we look at the structure, there we go, their numeric type. There's your 3 dimensions. Here's the list of actual values. I can tell already without doing type of that each of those values is going to be double. Yep, sure is. Okay. Now let's do something a little fun with class. It turns out things like class. What was the name of my matrix back here? W? Oh yeah. Things like a class can be changed. So it's just like a little sticky note stuck to the side of your vector. So you can always tear that note off, scribble over it, and put your own vector name. Now luckily, there's going to be, it's smart enough to know that if you do this for the simplest structures, it's really bad for more complicated data structures. If you rewrite the class, you have completely renamed the class, and functions won't recognize the class anymore. So if I have something called the foobat, I don't know why, or the, I don't know, let's call it Fairbanks 1 data structure, and that's its class. And I have a function that expects the Fairbanks 1 data structure, and I change the class to Fairbanks 2, that function's not going to recognize it anymore. It's not going to look for the right generic functions. So this could cause nothing but trouble. Luckily, for things as simple as matrices, it isn't really flaunting. Flout? I guess flaunt. Not flaunting the class. That's because the class of matrix is attached to it pretty strongly, so that if I create a new class name, it's going to do what's called inheritance, which we'll talk about later. So it'll really keep the old class name of matrix. It'll recognize it still as a matrix, but I can give it another sort of class also. Probably the dimension structure lets it be known as a matrix. So watch what I can do. I can rename its class. So right now the class of this thing is matrix. So I can go, I'm going to name it completely new. And if I created a new data structure, I could do this. So let's say I want to have some special functions that work in a special way with matrices. So then I'll say, okay, I only want them to work with specific matrices that are called Ron matrices. Okay. Now look. It probably won't show it here. Oh yeah, I have named a new type of object. It's called a Ron matrix. Luckily, it still has dimensions. It still has a vector. So because it has dimensions attached, I probably can get away with treating it. Oh, look at that. See? Oh, not Ron matrix. What's the name of it? The name of it's W. So you'll see it still works. So Luckily, in this point, it did something called inheritance, where even though it says it's a Ron matrix, it still recognizes that the fundamental structure is a matrix under there. Warning, warning, warning. That always won't be, not necessarily will always be the case, and if you change a class, you might break the functions that work with that class. Or it won't work with the object anymore. Instantiation of the object. So let me just be good and change it back. Class W equals matrix, and it'll be back to being a matrix. Okay. Let's look way back at X. There's one last attribute. Did we attach any attributes to this? Nope, we didn't. And this one was a vector of doubles. Yep. We can actually attach attributes to these. So one is names. We'll see later, there's a couple ways of attaching names. But remember, attributes are metadata. So I actually can give a name to each one of the slots in this vector. There's 4 slots. So I'll say okay. Okay, so now it has an attribute attached to it. If I look at the X itself, I've attached names to it. And if you look at the structure of X, you can see now, it's just like I said with the sticky note. Here at the top is the data structure itself. Okay, it's a named numeric vector with 4 things. Here's the 4 things. It has an attribute called names that are characters. The attribute itself is a character of length 4, so it's a vector of characters, and there they are. Well, I think I will stop here, and next time I will talk a little bit about lists, which are basically they're the extension. Lists and data structures are sort of the extension of matrices where you can combine non-homogeneous structures. So, for instance, I can mix very, very different types of objects into one data structure when I'm using a list. Almost all objects that come out of R functions are created by are actually lists with classes declared. So I will stop right now.